Together, we'll explore the nature of intelligence. Intelligence for machines. So what is intelligence for machines? Intelligence for machines could be said as a product of information processing. Now, intelligence for human beings could be different, but for machines, it's just a product of information processing. When I say information, I also mean data. So you specify the properties of output information, and then you specify it as a function of input information. Then it becomes a computational task, and we are interested in computational intelligence. So this kind of computational task can be solved by algorithms. So the answer to a computational task is an algorithm. Now, what kind of algorithm? So we have a bunch of varieties of algorithms, and some of these has the ability to learn. So we express our algorithms in terms of dichotomy between the one that has a learning ability and the one that doesn't have the learning ability. So the algorithms that can learn, those are AIs. And AI is kind of a program. I think we already know that we human beings are dangerous. The wealth of information and the growing knowledge that we have, it need only be misused once to end the entire project of humanity. Now, human beings are dangerous, and to that extent, AI is also dangerous. Now, the worry that AI is more dangerous than human beings, or the worry that AI is going to get away from us, this kind of worry is speculated by some computer scientists, non-computer scientists. So they think of ways of shackling AIs. That is the mistake. So I'm deeply unsympathetic to this kind of worldview. Now, the good news for the worried members of the planet Earth, those who are worried about AIs, is that our AI or machine learning or intelligent technology is not that far. We are not even at a level of human intelligence. We don't have a program that resembles human level intelligence yet. But look what I said, that word far. The metric behind the word far, the dimension of the metric behind the word far is not time. It need only be one breakthrough that can change everything. And we, first and foremost, are engineers and scientists. We can make that breakthrough. So to make that breakthrough, we need to understand what are the computational complexities of those learning algorithms so we can design better algorithms. Maybe at some point, those algorithms will design even better algorithms, and so on. That's how the progress of knowledge will proceed. Now, we would like to study this algorithm, and let me say that we'll be studying this algorithm in terms of the ones that has learnability. This learnability will be studied under two categories. Okay. So pack learnability and APAC learnability. The pack learnability, what does PAC stand for? Can anybody tell me?
Probably approximately correct.
Probably approximately correct, right? So the learning ability, one of those are probably approximately correct, and the other ones are agnostic pack learnability, agnostic pack. So I'll not give a very descriptive description or anything. I'll just tell you the gist of it now because you already attended 4 weeks of lecture, right? So we will study those in terms of loss. Okay. If a pack learnable hypothesis class has this amount of loss, meaning less than the epsilon, then we say that it is pack learnable. If it has more than that, probably it's not a pack learnable algorithm. Now, with pack learnability, there is something special about it. We suppose that there's no sample error in pack learnability. It is rather a very strong assumption. We'll rely this assumption for agnostic pack learnability. Now, we suppose that there is no sample error. Usually, there will be a term here that will have some sample error, So there is no sample error in path learnability. When we don't have it, because when the realizability holds, in short I'm writing it as realizability holds. What is this realizability? It simply means that it doesn't have any sample error, right? So sample error is 0. For agnostic path learnability, we are a little bit more practical. So we understand the real-life trade-off. So instead of claiming something impossible, which is not exactly impossible, but mostly it is, because we never know that there will be some sample error or not. So we are using a much more gentle approach. So the important distinction or generalization for these two kinds of learning ability I'd like to make is that APAC learning ability is a generalized version of PAC learning ability. Because we're doing here over the hypothesis class, we're trying to figure out that particular one hypothesis that has the minimum error, and that minimum error for PAC learning ability is 0. So we can, of course, claim that APAC learning ability is a generalization for PAC learning ability. Now, we'll be studying a bunch of those ideas along the way. Now, I don't want to discuss a lot about the ideas because you've already attended 4 weeks of lectures. But the goal for today's class is to solve all the problems that we have. So we will solve that, and any idea from the previous lecture that pops up, I'll briefly discuss, at least in a way that is easier for you to comprehend. Okay? Now, we'll go to the problem set, right? Okay, so I guess this is the first problem, right? 2.3, isn't it? Alright, so an axis on a rectangle classifier in the plane is a classifier that assigns the value 1 to a point if and only if it is inside a certain rectangle. This is the rectangle we're talking about. And then this rectangle, you see the region, right? And this, there's a smaller rectangle inside. I'll tell you the question as a story because the whole thing is so messed up, and actually not messed up. This is the standard way of describing a problem, alright? But what I will do, instead of reading it out in the class, because our class time is really short, what I will do, I will explain the question so that you understand, and then we will try to attack this problem. Now, okay, so the first one says that let A be the algorithm that returns the smallest rectangle and closing all positive examples in the training set so that A is an ERM. So our goal is to prove that the algorithm A is an ERM. Okay? Now, much noise. Okay, so let me describe the problem first, okay? The idea here is that we have a bunch of pluses, okay, and also a lot of minuses, right? Now, we would like to, our algorithm, consider our algorithm to be a rectangle, okay? The rectangle is an algorithm. So the way we'll do is that we will use that rectangle to catch all the pluses inside and minuses outside. That's the simple idea. Now, how can I do that? Looking at this picture, it's pretty easy. Just draw a rectangle, right? So all the pluses are inside and minuses are outside, right? Okay. Now what if we have some minus here, or some complicated challenge, like you want to fit that rectangle for all the pluses? What's going to happen is some minuses are inside. Then what we say that we have some sample error, right? Now, if we have some sample error, that is a problem, because our question is asking that find the ERM. ERM is the one that doesn't have any sample error. Now, let me draw even smaller rectangle. Now, probably we don't have any sample error. Here we have some sample error. Pluses, some minuses, right? But inside of it, there's no sample error. You okay with it? Cool. Now, for the first problem, 2.3, realizability holds, then the sample error is 0. Right? If the realizability holds. Now, if you look at the picture or diagram, you can tell that the smallest rectangle will have 0 sample error. Right? So, smallest has the smallest one will have 0 sample error. Now, we want to prove that that is an ERM. What is an ERM? Let's see the definition of ERM. By definition of ERM, we can say that ERM, the sample space, belongs to the argument. H belongs to H as H. So the idea for ERM is that it tries to find the minimum of the hypothesis from the class of hypotheses that gives us minimum error. And we know for ERM estimator that minimum error is 0. Okay? So if this minimum error is 0, now we can say that our algorithm A is an ERM estimator or ERM. Okay? So A is does it make sense? Yeah, I'll ask a specific question. Yeah.
I can get it.
Okay, so we're using an analogy here. Okay, we know if the realizability holds, then the error on the sample space is 0. Correct? Our training set is 0. Now, if we draw a rectangle that is the smallest, that also gives us 0 sample error, right? Our training error. Now, our goal is to prove that our algorithm A is an ERM learner. So, what is an ERM? The ERM is the hypothesis that gives us a minimum error over the training set. You get the idea? Now, for an ERM estimator, we know that the sample error of the sample space is 0. Now, if all of that satisfies, and if we compare and take it as an analogy that this gives us 0, and ERM also gives us 0, then can we conclude that our algorithm A is an ERM? That is the analogy that we use. Okay.